Good morning, good afternoon, good evening, depending upon what part of the world you are joining us from. Thank you for joining us. As Vanessa mentioned, today I'll be talking about a modeling of geothermal wells and systems at reservoir scale. So geothermal systems are systems that are designed to extract the energy from the surface of the earth. So Earth's core contains a virtually limitless amount of thermal energy, and this thermal energy manifests in the form of what we call a geothermal gradient. A geothermal system, as I mentioned, is a system designed to extract the geothermal heat of the Earth. You can think of a geothermal system as a giant heat exchanger that extracts heat from Earth's crust through circulation of a fluid. There are several advantages of a geothermal system. Geothermal systems happen to be environmental friendly. They have a super ultra low emission and very small environmental footprint. They're not seasonal, so unlike wind and solar, geothermal systems are not affected by weather or seasonal conditions, so they can operate throughout the year without any interruption. They are sustainable because heat in the crust is continuously replenished by the heat conduction from the mantle below it. And these systems are scalable and economical. Particularly with these systems, you will see that there's a rapid gain in efficiency and economy with increase in depth. So as I mentioned, there's a rapid gain in efficiency with depth. So for example, 3 wells at a 400 degrees Celsius depth can generate more power than 42 geothermal systems at 200 degrees Celsius depth. So as you go deeper, the temperature of the Earth increases and the efficiency of geothermal systems also increases. And this gain in efficiency immediately translates into gain in economy. So for ultra deep geothermal system, the cost of production is fairly low compared to conventional geothermal systems. So by going deeper, you can produce electricity and energy at much more economical rate, as shown by the various plots here. And there is an abundance of geothermal energy throughout the world. What I have shown here is the geothermal map of the United States, and you can see here there is abundance of geothermal energy in continental North America, particularly in the western part of the continent. So let's go through the life cycle of a geothermal well. So the life cycle of a geothermal well includes drilling. So drilling involves drilling of the vertical and horizontal section of the well. And during the drilling, engineers need to consider concepts like mud weight window, borehole stability, loss circulation, the typical concept that you use in drilling of oil and gas wells. Then you have to complete the wells, which involves installing the casings and putting the cementing around it. And during completion, engineers need to consider concerns like the stresses in the cement, the integrity of the cement sheath, and the zonal isolation. The stimulation, this is a step which is particularly specifically required for enhanced geothermal systems. So as I'll explain in later slides, that the enhanced geothermal systems are the systems that require fracking the reservoir. So in these kind of systems, you need to stimulate the reservoir by creating fractures. So in these kind of systems, you have to use an additional step of fracturing the subsurface rock by injecting pressurized fluid. And the typical consideration while performing stimulation of the reservoir rock is what is the size of the fracture, the trajectory of the fracture. If you're putting proppant, what's the proppant placement, and what's the fracture conductivity of the fracture created through hydraulic process. Once you have drilled the well and created the fracture, you initiate what we call fluid circulation. And the process of the fluid circulation basically involves circulating a fluid through the subsurface loop and extracting the geothermal energy. Typically in a geothermal system, you have an injection well and you have a production well. You inject the cold fluid through the injection well and you produce hot fluid through the production well. Once the well has run through its life cycle, the well is typically abandoned, means that you basically plug the well and decommission it. The plugging of the well involves putting cement plugs throughout the depth of the injection and production wells. And in this kind of work, the key consideration includes integrity of the cement plugs. So what are the various engineering considerations in design and execution of geothermal wells? So typically planning and execution involves inputs from multiple different experts. You need drilling engineers, completion engineers, and geothermal engineers. So drilling engineers are responsible for the drilling operation. They're concerned with pressure and temperature of the circulating mud or the fluid. They ensure borehole stability and safe mud weight window. Completion engineers are responsible for putting well casing and cementing. They're also responsible for putting hydraulic isolation if required, or plugging of the well upon the end of the life cycle. Then you have geothermal engineers. Geothermal engineers are responsible for ensuring that there is a high energy recovery factor. They're responsible for maintaining the efficiency per unit mass of the fluid circulated. They're also involved in the loop design if you're thinking of advanced geothermal system, or frac design if you're thinking of enhanced geothermal systems. They're also responsible for fluids and rates selection. Currently, different engineers use different types of software, and the disconnectivity of the software poses a challenge to or barrier to adoption of digital twins. And so drilling engineers have their own set of tools, completion engineers have their own set of tools, and geothermal engineers use their own set of tools. Typically, these different tools they're based on different technologies. Some of them are based on CFD, some of them are based on FEA. And because of that, it's not easily, or in sometimes not entirely possible to integrate the different software packages. So what you end up with is a disconnected system of simulations, and it poses significant challenges in seamlessly designing the system. And many times these softwares are procured from different vendors. That also poses difficulty in connecting these softwares. So how can we break these barriers? So in DESO, we are breaking these barriers by using a unified multiphysics system of simulations. These systems or simulations are based on one single technology, which is FEA. These are fully coupled methods which are seamlessly integrated in one framework, so you don't have to switch from one tool to another. All the different engineers, drilling, completion, geothermal engineer, can use the same set of tools, and these tools are developed in close collaboration with industry leaders. So we have deeply integrated the various requirements that come from industry operators. So what are the elements of the technology? So the technology has been implemented mainly through a number of special purpose elements. There are three key pieces of technologies that we have developed. One is for fluid transport inside the borehole. So we have developed special borehole elements that allow us to model the fluid transport inside the borehole elements. Then we have models for capturing pore elastic response of the surrounding rock, and it is captured through what we call a coupled thermal hydromechanical elements. We have also developed special models to capture the fracture of the reservoir rock in case of enhanced geothermal systems. And these fracture models are provided by specialized cohesive elements, and these cohesive elements also have thermo-hydromechanical coupling. In what follows, I'll give you examples of each of these technologies and how these technologies can be combined together in different ways to solve different types of problems. So these elements are like pieces of Lego, and you can combine them in different ways and purpose them to model different types of geothermal systems. For example, if you're just using a borehole element, you can use it to model the flow of the fluid through a geothermal well and how its temperature evolves over a period of time. You can combine borehole elements with the THM element, the thermo-hydromechanical pore-elastic elements, to model advanced geothermal systems. And you can combine borehole elements with the THM elements with cohesive elements, all of the three together, to model enhanced geothermal systems, which require hydraulic fracturing. So as you can see here, you can basically model different types of geothermal systems by combining these technologies in different ways. So let's take some examples of each of these technologies, starting with borehole elements. So as I mentioned, these are special purpose elements specifically designed to model the fluid flow inside a borehole. The borehole can also be a riser or a casing. The fluid can be static or moving. These elements provide pressure, temperature, and mass flow rates at every point along the borehole while enforcing mass, thermal, and pressure equilibrium. The fluid properties in these elements, like fluid properties like density and viscosity rheology, can be specified as a function of temperature. And here is one example where we are modeling the flow of a fluid through a geothermal well for different production rates, and you can see the evolution in pressure and temperature. The plot in the middle shows the pressure of the fluid as it travels from the bottom hole towards the wellhead, and you can see how the pressure evolves for different flow rates. On the right, I have shown the evolution of temperature of the fluid inside the borehole as it travels from the subsurface to the surface. The gray curve shows the geothermal gradient, and the various colored curves show the temperature of the fluid for different flow rates. So as you can see here, higher the flow rate, slower the change in temperature of the fluid. These elements also allow us to model different kind of ties between the borehole element and the reservoir rock. You can couple the temperature and pressure inside these borehole element with the outside reservoir rock, and you have different types of coupling available. The coupling can be a pressure only coupling, in which case you only couple the pressure degree of freedom between the borehole element and the reservoir rock. It can be temperature only coupling, where you're only coupling the temperature between the borehole and the reservoir rock. Or it can be pressure to temperature coupling, where you're coupling both temperature and pressure between the borehole and the reservoir rock. These elements allow us to, in terms of outputs, these elements provides us pressure, temperature, mass flow rate, total pressure, and friction pressure loss. And these elements support a wide variety of fluid behavior and rheology. So you can model different types of fluid behavior and rheologies. For example, Newtonian, power law. In non-Newtonian fluids, you can model Bingham plastic, Herschel-Buckley, and generalized power law fluids. So we use these elements to model or to design geothermal systems. That would be an example of how these elements can be used. Here is kind of an example of what we call an advanced geothermal system, where we are modeling the thermal exchange between the circulating fluid and the surrounding reservoir. And through this kind of simulation, we can predict thermal recovery as well as pressure loss for different circulation rates and fluid properties. And the way these kind of systems are, or this kind of simulations are put together, you start with geothermal gradient and the lithology of the reservoir. You create a mechanical earth model. You embed the borehole elements inside the mechanical earth model, and you connect or you tie these elements with the reservoir rock. You inject the fluid from the injection well, and you produce the fluid from the outlet or the production well. And as the fluid travels from the inlet towards the outlet, it gains heat through the interaction with the reservoir rock. And we can map the temperature of the fluid as it travels from the inlet towards the outlet, as shown on the plot on the right. So you can see here how the temperature of the fluid changes as it goes from inlet to outlet. And you basically map the temperature for the different segment of the well. For example, the segment 1 is your injection well, segment 2 is the lateral part of the well, and segment 3 is the production part of the well. You can also track the pressure of the fluid, and you can map the pressure losses that the fluid incurs as it travels through the borehole, as shown on the plot on the right. So in essence, you can track the temperature, total pressure, and the pressure loss of the fluid as it travels through a geothermal loop. Here is another example. In this example, I'm considering the flow of a fluid through a well bore. And in this case, we have a leak or an outflow in the wellbore, and we are able to show how that leak affects the temperature of the fluid inside the wellbore. So the plots on the right show the temperature of the fluid for different outflow rates. So the red curve is your geothermal gradient, and the various colored curves show you the temperature of the fluid for different outflow or leak rates. So as you can see here, as the you can clearly see the impact of the leak on the temperature of the fluid. Greater the amount of leak, greater the variation in temperature. Another thing you'll notice that you see the deviation in temperature only after the point of leak or outflow in these kind of simulation. So these kind of simulation can be used along with field measurement techniques like DTS to identify if there is a leak, and if there is a leak, identify the location of the leak. In a similar example, we can also model the fluid of temperature of a fluid inside a wellbore with an inflow. So if you have multiple sources of fluid, how those inflows affect the temperature can also be simulated and captured through this kind of simulation. So here we have a borehole system with fluid infusion, and we are able to track the temperature of the fluid throughout the borehole for different inflow rates. So again, just like before, you would be able to see the effect of inflow on the temperature profile of the fluid. Different levels of inflow affect the fluid temperature to different extent. So the green curve, for example, here is the case where there's no inflow. The orange curve represents 10% inflow, and the blue curve represents the 20% inflow. So greater the amount of inflow, greater the variation in the temperature of the fluid. Let's look at now some of the drilling and completions applications. So one of the things that is possible within Abaqus is to model the entire structure of the subsurface rock, and then use a poroelastic formulation to predict the in situ stresses inside the subsurface rock. And these kind of formulations allow us to capture the subsurface lithologies and material anisotropy. And here is kind of an example where we are using our poroelastic formulation capabilities to predict the various components of stresses inside the rock. So you see overburden stress, that's the blue curve. You can see the SH-min or the fracture gradient, which is represented by the orange curve, and the pore pressure, which is represented by the gray curve. So you can capture in situ stresses and pore pressure using a poroelastic formulation. We can also assess the stability of the borehole as it's being drilled. We can use our poroelastic formulation to obtain the pre-drilled and the post-drill state of stress. And we can use this information to create envelopes of shear instability and fractures. And that information can be used to determine what we call mud window. What you see here is the pre-drilled state of stress. It's obtained in a similar fashion that I talked about in the previous slide. And then we can also model the process of drilling as it happens. And we can calculate the state of stress around the borehole, and that information can be used to calculate what we call a mud weight window. We also have abilities or capabilities to model the borehole breakout. We have a library of a variety of soil plasticity models that allow us to simulate the wellbore breakout process. We have plasticity models like Moore-Coulomb failure, Drucker-Prager plasticity model, and with these models, we can model the breakouts of the wellbore in case of wellbore instability, as shown here. And these simulation results compare very well with the field measurement, as shown here. We can also model the failures of the cement sheath. So in case of geothermal systems, the fluid flow through the borehole can cause the casings to cool down over the period of time, and these cooling can cause the casing to shrink, and upon sufficient cooling the casing can start to snap off from the cementing. So what I've shown here is the temperature of the casing as a function of time, and as you can see here, over a period of time the casing kind of cools down, and as a result of this cooling down the casing kind of shrinks, and over a period of time the casing can start to debond from the cement sheath. So using this kind of simulation we can predict the onset of cement casing interface failures. We can also identify the temperatures at which such failures are likely to happen. Another type of failure that can happen in the cementing in the geothermal systems is the fluid invasion. So when you are injecting the fluid, the injected fluid can invade into cement casing interface, and this kind of injection can lead to interfacial fracture at the cement casing interface as shown here. So in this example the fluid is kind of invading into cement casing interface, and as a result of that invasion you have a debonding between the cementing and the casing. And these kind of debonding can be detrimental to your zonal isolation process. They can ruin your zonal isolation. So it's important to assess the likelihood of such failures and prevent it if possible. We can also model the cement sheath failures under high pressure and high temperature. So many of these geothermal wells, they tend to be very deep, and the temperature and pressure conditions at such depth can be very high. And under high pressure and temperature, the cement sheath can experience stresses that cause the failure of the cement sheath as shown here. So in this example, we are showing the failure of the cement sheath in response to high pressure and high temperature. And typically in these kind of failure, the cement sheath experiences multiple fractures, and these kind of fractures require XFEM kind of technology to be modeled. So I'm gonna next show some examples of advanced geothermal wells. So in advanced geothermal wells, basically you have what we call a subsurface loop that runs through the depth of the earth. Typically you have an inlet well and an outlet well, and these two wells are connected by what we call a lateral section. You inject the fluid from the inlet section and you produce the fluid from the outlet section. Between inlet and outlet, the fluid travels through a significant distance, and during this travel, it gains heat from the temperature of the subsurface rock. So as a result, the outlet fluid can be significantly hotter than the inlet fluid. So we can model the temperature of the fluid as it travels from the inlet to outlet, as shown here. You can see here there's a significant gain in temperature as the fluid goes through a geothermal loop. The temperature rise can be in excess of 100 degrees Celsius depending upon the geothermal gradient and the length of the geothermal loop. Our simulations allow us to capture the evolution in temperature as well as in pressure of the fluid. We can model different flow rates or different injection rates. So we can, for example, assess the outlet fluid temperature for different injection rates. Typically, as the injection rate increases, the gain in temperature decreases. But the amount of heat recovered, it's kind of a product of gain in temperature and the mass flow rate. So we can calculate the heat recovery factor by multiplying the change in temperature with the mass flow rate and the specific heat of the fluid. So using the simulation, we can identify an optimal injection rate that gives us desired heat recovery from these kind of systems. We can also use simulation to explore different designs of the geothermal well. So for example, we can compare single loop system versus multiple loop system, as I've shown here. We can map the temperature for these kind of different designs and compare what kind of heat recovery factors we can obtain from different designs. So here I have shown a comparison between a single loop design and a multiple loop design. In case of multiple loop design, what I've shown here is the temperature of the fluid for the different laterals. So you can see here, you can clearly see the difference in temperature for the two laterals. You can also see the jump in the temperature of the fluid when the fluid from the two laterals merge at the production well. We can also model the uh, the spacing, or we can also model the spacing of different laterals. We can identify the optimal spacing for these laterals. Typically in this kind of systems, if the two laterals are too nearby or too close, they can eat away into each other's efficiency, and as a result of which, for closely spaced well, you can see a degradation in temperature over a period of time. For sufficiently far apart wells, you don't see much interaction between the different wells, and in that case, the degradation in temperature output is rather low. Using this kind of simulation, we can identify the optimal spacing for the different laterals that gives us the most optimal performance. We can also predict the attrition in thermal capacity over a period of years. Typically, in geothermal systems, over a period of years, there is a cooling of the near borehole region, and that cooling can lead to attrition in the thermal capacity of the system. Using our simulation, we can predict that attrition. For example, I have compared the system performance after 1 year and 30 years, and you can clearly see that there is a deterioration in the system performance because of the near borehole cooling. So our simulations allow us to capture that deterioration, and we can identify a kind of a cutoff point beyond which there is a significant deterioration in the thermal capacity that the well should be abandoned. Next, I'm going to talk about enhanced geothermal systems. These are types of systems that require fracturing of the reservoir rock to improve the efficiency of the system. So within Abaqus, we have a very robust fracture modeling capabilities. These capabilities are provided by a special class of element known as coupled thermo-hydromechanical cohesive elements. These elements allow us to model these changes in temperature and pore pressure coupled with the mechanical stresses. We can model the damage initiation and evolution in the reservoir rock. We can model the fluid flow inside the fracture, and this type of flow is known as gap flow. We can model the fluid loss through the fracture phases, and it's known as leak off. And we can also model the proppant transport and placement inside the fractures. These elements and these technologies have been significantly validated against experiments, extensively validated and verified against a series of in-house experiments. And this is an example of one such validation. In this validation, we have looked into fracture growth behavior under different interlayer stress contrast. So the rock is divided in several layers, and the different layers are subjected to different amount of stresses, and the difference leads to what we call interlayer stress contrasts. This experiment kind of explores the fracture behavior for different interlayer stress contrasts, and it was seen in the experiment that as the interlayer stress contrast kind of decreases or goes down, the fracture geometry changes from a pear-shaped to a fixed-shaped. So we simulated these various scenarios using our fracture modeling capabilities and compared the results with the experimental ones. And we were able to see that we were able to show that the response from the simulation compares very well with the experiment. So here you can see how the various the simulated response for the various interlayer contrast compare with experiment, and you can see close level of confirmation between the simulated and the measured response. So we can model fracture growth in different types of stress environments. So in the subsurface rock, the stress environment can be very complex, and we have the ability to model fracture growth under different types of stress environment. Here I have shown the fracture growth behavior for 3 different types of in situ stress environment. On the leftmost side, you see the fracture profile for a constant stress environment. In the middle panel, I have shown the fracture profile for a stress in situ stress environment with what we call a stress barrier, and the stress barrier leads to what we call containment of the fracture. So the fracture merely remains contained inside the stress barrier zone. On the rightmost panel, I have shown the fracture growth behavior for a stress profile that is kind of declining with height. And in that kind of scenario, you can see the fracture tends to mainly grow in the height direction. So we can model fracture growth behaviors for different stress profiles. We can also capture, because these elements have full thermo-hydromechanical coupling, we can capture the coupling between the fluid flow and structural fields. So for example, we can model the frac growth profile for different viscosity fluids. So in this example, everything is same except the fluid viscosity, and you can clearly see how fluid viscosity affects the fracture growth behavior. Particularly for low viscosity fluid, the net pressure is not high enough to cause the fracture to grow beyond what we call a stress barrier. In contrast, in case of high viscosity fluid, the net pressure is significantly higher. As a result, the fracture can broach through the stress barrier. So you can clearly see the difference in the fracture growth behavior, mainly arising from the fracture fluid viscosity. So we can capture those kind of details with our technology. We can also capture the coupling between thermal and structural fields. Again, I want to emphasize that these elements have full thermo-hydromechanical coupling that allow them to capture the effect of temperature or the fluid flow. In these examples, I have shown the effect of injected fluid temperature and how it affects the fracture growth behavior. On the left panel, I have shown the example of what I call cold injection, where you're injecting cold fluid into a rather hard formation, and we are trying to show what kind of fracture growth behavior emerges out of those kind of injection. On the right, I have shown an example of what I call hot injection, where you're injecting a fluid that is hotter than the reservoir rock, and we are also able to see in that case how the frac growth behavior is affected by difference in fluid temperature. So you can clearly see different fracture profiles emerging from difference in the fluid temperature. And here I have shown the treatment pressure for different stress environments. So we can model multi-stage hydraulic fracturing. So in many of enhanced geothermal systems, you have basically a number of fractures that are being created simultaneously, and these fractures are used to connect the injection well with the production well. When multiple fractures are propagating simultaneously, they can interact with each other, and it's known as, this phenomenon is well known, is known as stress shadowing. Because of the stress shadowing, some of the fracture can be suppressed, leading to lesser number of fracture than you would expect. So here you're seeing an example of stress shadowing in a system of 3 fractures. These are tightly spaced fractures, meaning that they are located very close by. And because of the interfracture interaction, you can see the middle fracture is being suppressed while only the outermost fractures continue to grow. We can so in these kind of systems, we can also kind of capture what we call the fluid distribution. What's the fluid distribution between different fractures? So in this particular examples, you'll see that after a certain point of time, only there's a non-zero flow rate in fracture 1 and 3, which refer to the exterior fractures, and there is no flow into the interior fracture. And that is happening due to the fact that the middle fracture is being suppressed due to intrastage stress shadowing, and as a result of which, after a certain point of time, this fracture stops accepting any fluid. So you only see fluid flow only in the exterior fracture and not in the interior fracture after a certain point of time. We can also track the temperature of the fluid as it travels inside the fracture. So here I have shown the contours of fluid temperature inside one of these fractures. So you can clearly see how the temperature of the fluid changes as it goes from entry to the tip. So there is like gradual rise in the temperature of the fluid as it travels inside the hydraulic fracture. And these kind of analysis can be used to kind of determine what is the optimal length of fracture for an enhanced geothermal system. Another capability that we have available in thermo-hydro-mechanical coupled cohesive element is the proppant transport and placement. So typically when you create a fracture, you need to pack these fractures with the sand particles in order to keep them open after the injection has kind of stopped. So in order to keep the fractures open, you have to pump this sand slurry. The sand slurry goes and sits between the fracture faces and prevents them from completely closing upon upon the shut-in of the flow. Now, as this propellant goes inside the fracture, it can um, settle due to the effect of gravity, meaning that, and I'll go back to the previous slide, meaning that the propellant doesn't completely occupy the created fracture, but it only kind of occupies a portion of the created fracture because of the gravitational settling. Now, the settling is caused by an interplay of four different forces. So you, of course, have gravitational force. This gravitational force acts in the downward direction and is the primary driving force for settling. But then you also have the buoyancy force, and this force acts in the upward direction and it opposes the gravitational settling. In addition, you have viscous drag. It acts in opposite to the particle motion, and it also opposes the process of settling. And then you also have a particle jamming. So when the particles are too nearby, there's this interparticle friction that also reduces the particle mobility. So in Abaqus, we have a functional model to account for these four forces and calculate the settling velocity. The model looks something like this. Here you basically can see the effect of gravity, effect of viscosity, effect of particle jamming, and effect of particle size. Now, the way this model is set up, there are two unknown parameters in the model, M and N, right? That basically determines the behavior of a specific propellant type. So different propellant type can have different values of M and N. The way we determine this M and N parameters is by calibrating our model against experiment. So what we have done here is we have calibrated our model against what we call slot test simulation. The slotted test basically involves injecting a sand slurry between two flat plates and monitoring the settling patterns. By comparing the simulation response with experimentally observed response, we can tweak the value of M and N such that we get a close confirmation with experiment. So by calibrating our simulation against the experiments, we can determine the value of the coefficient M and N for a given propellant type. So by these kind of comparisons, we have a fully calibrated model for the settling velocity for a given propellant type, and we can use that model to predict the settling behavior under different injection scenarios. Here is one of the scenario where basically the injection rate is very high and the propellant concentration in the injected fluid is very high. And this kind of scenario can lead to what we call tip screen out and creation of a frac pack. So here we have modeled hydraulic fracturing with a very high proppant concentration, and the high proppant concentration causes the tip screen out, eventually resulting in what we call a stagnant fracture and creation of a frac pack. So because there's a high concentration of the proppant starts shielding the frac tip from the frac fluid, as a result of which the fracture stops growing and the proppant starts filling the entire fracture over a period of time. So as you can see here, the proppant is kind of filling the fracture and resulting into creation of what we call a frac pack. And here's kind of an animation of the process. So initially we are creating the fracture. The fracture is growing. Once we start injecting the sand slurry or the proppant starts shielding the crack tip from the rest of the fluid pressure, as a result of which the fracture stops growing and the proppant starts filling the entire fracture over a period of time. And what you end up with is with a fracture cavity fully filled with proppant. Here is an example where we have shown the process of proppant settling. So this is a two-step process. First, you create a fracture uh, using some kind of a frac fluid without proppant. In the second step, you start injecting a sand slurry or proppant into the fracture. And as you can see here, because of the effect of the gravity, the proppant start immediately settling inside the fracture. And as a result of which, and I want to pause here, as a result of which, um, as a as a result of which the proppant particles occupy only a portion of the fracture, only the lower half of the fracture, as you can see here, and upper of the half of the fracture remains unoccupied. So what's going to happen is, because the upper half of the fracture is unoccupied, as you shut off the flow, that part of the fracture completely closes. The only part of the fracture that remains open is the lower part of the fracture, because it has received the proppant. So so what I just showed was the proppant placement inside a fracture. Um, we can use that information to model what we call a propped fracture width. So if you look at the middle panel, it shows the propped width. And you can clearly see here the part of the fracture that doesn't receive any proppant. It completely closes, and only the part of the fracture that only the part of the fracture that receives proppant remains open. So we are able to kind of map the propped width for the entire fractures, and we can predict what is the width of the part of the fracture that remains open. And we can use that information to create a map of what we call proppant pack conductivity. And this information basically tells you, basically how easily the fluid can move inside the fracture. So that information is provided by the fracture conductivity map. And this fracture conductivity map is ultimately going to determine the connection between the injection and the production well. So as I had mentioned a couple of slides ago, in an enhanced geothermal system, you have an injection well and a production well. This production and these two wells are connected by fracture. And this fracture is filled with proppant, and the conductivity of the proppant is gonna kind of determine the extent of, or the ease of hydraulic communication between the injection and the production well. So basically, these simulations can basically allow us to capture some of the very intricate response of geothermal systems or enhanced geothermal systems that ultimately determines their efficiency. And so with that, I will conclude my presentation. We have 15 minutes for any questions that might arise from the audience.